Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last time, where we were trying to draw the magnetic lines of force produced due to the interaction between two magnetic lines of force. So we have the magnetic lines of force produced due to a current carrying conductor in an external magnetic field produced by two magnetic poles, which could be due to any reason. Now, if you combine these two, we had found that what we get is this slightly distorted magnetic field, but what is important is that this magnetic field, due to its distortion, results now in a magnetic force, and that's what we'll talk about in this lecture. And of course, if you want to know why we are doing all this, the reason is because we concluded, or rather we wish to find out how we can determine this electrical torque. Because if we can find out this electrical torque, we can then find out how the speed of this motor changes with respect to time. Because speed of the motor is the difference between the electrical torque and the mechanical torque as an integral with respect to the moment of inertia of the machine. So let's now go back, and as before I start the lecture, that a little bit of brief background, that if you're interested in these kind of video lectures but you would like something a little more comprehensive, I do have full-length courses which you can find on my website, which is pythonpowerelectronics.com. This is the home page of this project and contains almost all the information that you need. If you click on this button Learn, it takes you to the list of courses. So as of now, I have 5 courses. The very first course is simulating power electronic circuits using Python, and in this I talk about the basics of how you can use Python and Python power electronics to simulate power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the signal package within SciPy to analyze and design filters for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to model and simulate magnetic components such as inductors, coupled inductors, and transformers. And the fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package to analyze and design controllers for power engineering applications with the example of a single phase inverter connected to a single phase grid. And the very last course I have is a free course, which is Why Specialize in Power Electronics, and this is targeted towards either junior undergraduate students or even high school students who are yet to choose their domain of specialization. And the purpose of this course is to talk about some of the challenges and opportunities available in power electronics. So all these courses are available on 2 platforms, that is Decibels Lab and Udemy. If you click on any of these buttons, it will take you to the link for this course. The link for this page is available in the description of this video, so please do check it out if you're interested. So with this, I'll return back to my lecture. So as we were already saying, a little bit of brief background, that, or rather recap, that the circular magnetic lines of force, and the reason it is circular is because we are looking at the top view, right? This is a side view of a conductor. The conductor is vertical, and these lines of force are perpendicular to the plane of the conductor, which means they are horizontal. So if we look at this entire thing from the top, then in that case we see that the magnetic lines of force, which should have been circular, are now distorted, which means they are flattened at the bottom and they are elongated at the top. Right? Now, of course, this is because of the direction of current and the direction of these magnetic lines of force and the direction of this external magnetic field. Of course, I would encourage you to change these if possible. For example, if you reverse these two and you bring the south pole to the left and the north pole to the right, then the external magnetic field will be from the right to the left. Right? So this entire thing will change. In that case, you will see that this distortion is exactly the reverse. The flattening will happen at the top and the elongation will happen at the bottom. Right? And at the same time, you can also reverse this current as well. So if the current, instead of moving in the upward direction, if it is moving in the downward direction, then the magnetic lines of force will still be in the horizontal plane, but instead of going in the counterclockwise direction, they will be in the clockwise direction. So you can try to map that out also. So all these mappings will result in different types of distortions which you can see here. So I just delete this. Now, if we were to say that because of this distortion, how is the magnetic force produced? Because we've already seen that because of an interaction between magnets. Okay, this is interaction between two magnets, not electromagnets, just two plane magnets, the way we used to do as children, right? In such a case, what happens? And we've already seen that when we bring together two opposite poles, they attract. And when we bring together two similar poles, they repel. This is something we've known already as children. Now, what is important to know here is, when is there a repulsion? When is there an attraction? Now, as you can see here, the magnetic lines of force are extremely concentric and they are pushing each other away, almost like, for example, when you have two sets of waves which are colliding together, these tend to sort of push each other away, or rather push themselves upward. There's a huge foam of water upwards. In such a case, it's similar here as well. The magnetic lines of force, we don't see it, but they're almost like waves of water. So you can think of waves of water crashing into each other. The result is there is a magnetic force produced, which quite often results in this huge wave of, or rather wall of water, right? And here too, the similar thing happens. When we bring together these two north poles, because there is this huge concentration of magnetic lines of force in this region between these two magnets, and they are pushing each other away. And that's important because magnetic lines of force cannot intersect, right? You can't have two magnetic lines of force crossing each other. They will therefore push each other away. This impact of pushing each other away results in a magnetic force which repels these two magnets. So there's a force in this direction from the right to the left, and there is a force in this direction from the left to the right, which causes these two magnets to move apart. Now, in this case, right, when they are being attracted, it is exactly the opposite. You see here, there is a concentration of magnetic lines of force, but if you look, this entire region is now sparse, very, very sparsely populated by magnetic lines of force. Right? The reason is because now these magnetic lines of force are going directly from one north pole to the other south pole. The result is, when you have this sparse or rather low density of magnetic lines of force, the result is you have an attraction. Right? These two magnetic poles start being attracted to each other, because of which there is a force which pulls them together. So in the similar manner, if we were to go back to our diagram and figure out what happens here, you will see that because of this elongation here, right, the magnetic lines of force are elongated at the top, this density of magnetic lines of force is low at the top. And because they are being squished at the bottom, the density of the magnetic lines of force at the bottom is high, right? The result is, you see these two magnetic lines of force, there is a huge density here, right? There is a huge density here, and because of this huge density, these tend to push each other apart. So there is a force which is being produced which pushes this upwards, right? There is a force pushing this conductor upwards. And similarly here, because there is a low density, this elongation of magnetic lines of force, and also here too, these magnetic lines of force will be wider apart, spread wider apart. The result is there is a magnetic lines of force there is a mechanical force which pulls this conductor upwards. The result is there is a net force acting on this conductor in the upward direction. So let me just draw that. So there is a force in this direction, and there is a force in this direction. The force here is due to the high density of magnetic lines of force. These are all pushing each other away. And here too, the force is rather more due to an attraction, because there is a low density of magnetic lines of force which results in a pull effect. So here there is a push, here there is a pull, right? So the result of all this is, that now, because we have brought together a current carrying conductor in an external magnetic field, there is now a mechanical force acting on this conductor, right? There is no actual moving force here, or rather there is no human being moving this thing. There is no human being that is moving this conductor. All we are doing is placing this conductor in this external magnetic field, and due to the interaction of these two magnetic lines of force, there is a mechanical force, right? A mechanical physical force that is being produced on this conductor, right? And this is something which was noticed a long time back by, of course, and which became the force law, the Ampere's force law. So for this, the question then you might ask is, if we have such an interaction, that is, if we place a current carrying conductor in an external magnetic field, how would we determine the mechanical force? Do we always have to draw these kind of magnetic lines or these kind of flux diagrams? Now, the simple way is, you can see, and this is something I would encourage you to do, if you try out different combinations, that is, as I already said, switch the directions of the external magnetic field by switching these two poles and reverse the direction of current, you will find that you can map this interaction for every case. And in every case, we can determine what will be this mechanical force that is produced on this conductor in every case. So for that reason, there is now a law to determine the direction in which this mechanical force exists. What is important to remember is this magnetic field and this magnetic field are in the same plane. So if we assume that these magnetic lines of force are all in the horizontal plane, and so is this magnetic lines of force, then in that case we see here that this force produced is now perpendicular to the conductor. This is the conductor, right? Because this is a top view. So there is a external magnetic field from the left to the right. There is a current flowing from the bottom to the top, and there is now a magnetic line, or rather mechanical force produced, which is now perpendicular to both of them. So how do we determine this law? This law is called the Fleming's left-hand rule. So to find out about Fleming's left-hand rule, let's go to a web browser and let's do a Google search. I guess I wrote it wrong. Yes, Fleming's left-hand rule and right-hand rule. So there are two. Interesting. Oh, I'm sorry, I clicked a very local link which is not accessible. Yeah, so this is Wikipedia. This is Fleming's left-hand rule. So there are two rules that Fleming came up with. There is a left-hand rule and there is a right-hand rule. The left-hand rule is what you use when you want to determine the direction in which mechanical force is produced when a current carrying conductor is placed in an external magnetic field, which is our case here, right? What we are doing is we are placing an current carrying conductor in an external magnetic field. If, on the other hand, we wanted to find out what will be the direction of current if a conductor was moved in an external magnetic field, then we use what is called as Fleming's right-hand rule, which is the generator rule. So this left-hand rule is what is also called as the motor rule, because we want to find out the direction of the mechanical force, right? If a mechanical force were to be existing and we want to find out the direction of induced current, in that case we use the right-hand rule, but that comes much later if we talk about generators. For now we're just talking about motors. So very similar, or rather in a similar way to the right-hand thumb rule that we used, here however we got to use 3 different fingers, all of the left hand, So we have to hold these three fingers such that they are all perpendicular to each other. Alright, that's very important. They all must be perpendicular to each other. That is, you see the thumb here is here pointing in the upward direction. The forefinger is pointing in, let's say, one direction, maybe from the left to the right. In that case, this middle finger is now pointing towards you. If you hold this hand, your left hand, in such a manner, these are the directions in which these three fingers must point, right? And it's very important. All three fingers must be at 90 degrees to each other, right? If you bring these two, it doesn't look like it here because you're now representing something in 3 dimensions, in 2 dimensions. But it's very important that this middle finger, because you can see that the thumb and forefinger are perpendicular to each other because this is roughly perpendicular. But this middle finger has also to be perpendicular to both the forefinger and the thumb, right? So in that case, if the external field, direction of external field, is indicated by the forefinger and the direction of the current is indicated by the middle finger, then the thumb indicates the direction of the force, right? This is Fleming's left hand rule. So let's now go over to our diagram and find out how that will be. If I now point, right, so I would say use your left hand here. My left hand, I am using the forefinger from the left to the right because the forefinger points in the direction of the magnetic field, external magnetic field. The middle finger is now going to point in the direction of current. So I have to now twist my hand, or rather just my hand, such that my middle finger is now upwards, right? So my forefinger continues from the left to the right and my middle finger is now upwards. In such a case, my thumb, you will see, is now pointing away from me, right? And if you look, that is exactly the same as the direction of the mechanical force. So Fleming's left hand rule is just, you could say, a conclusion of all these mechanical interactions, or rather interaction between the magnetic fields that produces mechanical force, and is one single law that will always determine the direction of mechanical force if you were to place any current carrying conductor in an external field, right? So this law is extremely convenient whenever you want to find out what will be the force that is produced on a conductor or a current carrying conductor. That's very important. It must carry a current, because only if it carries a current will it produce its own magnetic field, and this magnetic field interacts with the external magnetic field. So let's come back here, and we see here that we can now use this law, Fleming's left hand rule, for finding out the direction of the mechanical force, right? Now, very important to remember, do not use your right hand rule. The right hand rule, as you can see here, it is for generators. That is, when you are moving a conductor in a mechanical field, right? It could be due to it could be a thermal generator where the motion is happening due to burning of fuel, or due to hydroelectric, or due to nuclear, or any, right? But it's important that when the motion is producing a current, in that case you have a generator, and when you have a generator you must use a right hand rule. Here we do not have a generator, we have a motor. Therefore we must use Fleming's left hand rule. So do not use your right hand, use always your left hand. And you can see there is a physical basis too. You can read it here. The physical basis is the same as what we talked about in our magnetic flux diagram, that it is due to the interaction between two magnetic lines of force, right? When you have one set of magnetic lines of force and you have another set of magnetic lines of force, these two will interact, and this interaction produces the force, just as we saw the force being produced due to two simple magnets. Only thing, we have taken these cases and made it slightly more complicated for the case of a current carrying conductor. So the previous case, that is what we talked about here, was the case of simple magnets. Here we are talking about electromagnets, right? That's the only difference. So now that we have established Fleming's left-hand rule and how Fleming's left-hand rule can be used here, now we are going to take this discussion to our motor, and in the motor we are now going to try to find out in which direction the force is going to be applied due to this interaction between magnetic fields. So this lecture has already gotten pretty long, so I will stop it here. In the next lecture, we will take these learnings and we will take this Fleming's left-hand rule that we have come up with, and we will now apply it to motors. The reason for doing all this is that I didn't want to jump straight and show you this Fleming's left-hand rule. Rather, I wanted to show that this Fleming's left-hand rule is basically nothing more than just a conclusion of different cases of how, if you place different types of conductors, let's say current carrying conductors in external magnetic fields, in each and every case we can map out how the magnetic field will look like. And depending on how the magnetic field will look like, we can always determine what is the nature of mechanical force. So if we take together all possible cases, we can always find out what will be the mechanical force, and this Fleming's left-hand rule is basically nothing more than just a convenient law, so that we don't have to draw these flux lines every time, right? We don't have to draw these flux lines every time. We can just use the law. But the law is basically eventually just a conclusion of this interaction. That's all there is, right? So with this, I will end this lecture. If you have any doubts, please do either send me an email or message me on social media or comment, whichever is your preference. Otherwise, I will see you next week, where we will use Fleming's left-hand rule in an actual motor diagram that we drew before and determine what will be the nature of mechanical force depending on the position of the rotor. Thank you so much for listening, and goodbye for now. See you soon.